Chapter 19, Lecture 2. Next section we're going to talk about is p-values and decisions, what to tell about a hypothesis test. This highlighted sentence is extremely important. How small the p-value has to be to reject the null hypothesis is completely dependent on your context. So p-values could be high or low depending on what it is you're working on. Now, if you were testing whether or not a musicologist could tell the difference between a couple of pieces of music and you get a p-value of 0.011, you might be willing to accept the fact that she really knows the music. The null hypothesis would be that she would be right 50% of the time choosing between two musicians. The alternative hypothesis would be that the true proportion that she gets right is greater than 50%. So this p-value is low enough you'd probably conclude that she can tell the difference between the two composers. Now, the second example they have, someone claiming they can control flipping a coin with their thoughts. You get a p-value of 0.011. That might not be low enough for you to reject the null hypothesis because it rejects long-standing scientific beliefs and or results. So a lot more evidence would be needed before you would conclude, you would reject the null hypothesis that he cannot, or she, or whatever, cannot control physical objects with their thoughts. Okay, so another issue is the importance of what you're testing. Testing whether the proportion of students who hold part-time jobs has changed. Okay, I mean, that's important, but it's not life-threatening. You'd probably be okay with a p-value of 0.05 or less. On the other hand, if you're checking out something that's like rivets in an airplane wing, and you want to test the hypothesis that there's nothing wrong with them, then you'd probably want that, or that they're okay, yeah. You'd want the p-value to reject that to be really low, okay? And okay, I'm sorry that the rivets don't have any problems. Okay, before you reject, let me start over again. The null hypothesis would be, since there previously were problems, the null hypothesis would be that they are faulty. And before you would accept evidence that would cause you to reject that is to think that the rivets are okay, you would need a very, very small p-value. So to repeat, because I said it wrong the first time, in the second example, the null hypothesis would be that the rivets are faulty because they were faulty in the past. It follows the doctrine that nothing has changed. You've made some improvements in the process, and now you're claiming that they're okay. The alternative hypothesis is that they're all right. You would need a very, very low p-value before you would reject the null hypothesis that the rivets are defective. The conclusion about any null hypothesis should always be accompanied by the p-value. If you reject the null, follow up your test with a confidence interval for the parameter of interest to report the size of the effect. Okay, just checking. A bank is testing a new method for getting delinquent customers to pay their past credit card bills. They used to send a letter costing about 40 cents. That works 30% of the time. Now they have a new method. They set up sending somebody a DVD to help them set up a payment plan. Developing and sending the video costs about $10 per customer. What is the parameter of interest? The parameter of interest is the proportion of customers that set up a payment plan that respond to the letter. Okay. So the null hypothesis is that the proportion of customers that respond is 0.3, p equals 0.3. The alternative hypothesis, since you hope to have improved performance with the video, would be p is greater than 0.3. Okay, you set up the experiment. They mail it out to randomly selected delinquent customers. They get a p-value of 0.003. Okay, now what does the p-value mean? The p-value is the probability of p hat occurring randomly, assuming the null hypothesis is true. The lower that the p-value is, the less likely it is that the null hypothesis is true. Now, this is a pretty low p-value, 3 out of 1,000. So with the p-value this low, you reject the null hypothesis. There is evidence that the DVD has increased the proportion of customers who pay. The statistician tells the bank management the results are clear and they should switch to the DVD method. You agree. What might else you want to know? Well, you want to know what is the increased rate? You want to do a confidence interval to get some idea of what the actual new rate is, and then see if that brings up in enough revenue, the increased number of customers paying, brings in enough money to justify the much more expensive method of sending out a DVD. The letter costs 40 cents. The DVD is $10. That is what? Over 20 times as expensive. 25 times as expensive, as a matter of fact. Okay, moving on. Now we're going to do a step-by-step example on the home field advantage. Okay, is there a home field advantage? Question. Could the deviation from 50%? So it looks like there's more home field wins than away wins. Could this deviation of 50% be explained from just natural sampling variability, or is it evidence to suggest that there really is a home field advantage? Okay, so on the right, you're going to state what you want to know. You state your data. The variable of interest is whether or not the home team won. Height.
Do you have the keys to the office?
Yes, I do. Okay, so we're investigating home field advantage. So the null hypothesis is going to be that the proportion of games won at home is 50%. Now, based on the evidence that has been gathered, it appears that we're going to claim for the alternative hypothesis that the true proportion is greater than 50%, greater than 0.5. All right. Now, here is a discussion of independence. And this needs looking at, and you need to look this over and get a handle on what they're talking about with the discussion of independence. I think what they're calling in here is the law of large numbers. Over the long haul, the games are going to be independent from each other, and obviously they're taking the games from the whole season. So this is like a cluster sample. So they're not selecting games randomly from a whole bunch of different seasons or whatever. They're hoping that the season is representative of all Major League Baseball games in the past and the future. So that's a good qualification of where the data comes from. Okay, the 10% condition and NP and NQ. Okay, now don't forget this sentence. The conditions are satisfied, so the sampling distribution is normal. Now you're going to name the test you're going to do a 1 proportion, because that's what you're dealing with, 1 proportion. You're using the z-score, so it's a 1 proportion z-test. All right, now you're going to show your mechanics here, the null model, normal distribution, standard deviation of p hat. Now you don't have to show the formula, although when you're doing the homework, it's probably a good idea to do it. So you're going to use, you're no longer using p hat. You use p hat when you're doing a confidence interval, when you don't know p. But we have p sub 0, which is simply the population parameter as it is expressed in the null hypothesis. So it's a square root of p sub 0 q sub 0 over n, and you can see it's quite low, 0.01. And p hat is the number of home victories over the total number of games, 1295 over 2530, which is 0.5329. Okay, so now we have we have our observed p hat, and we have p. So here's p in the middle, and p hat is 0.5329, which is over here. And this is, I don't know what happened here. Anyway, so you can see it's out in the tail. So 0.5329 minus 0.5 divided by 0.010143 is going to be a z-score of 3.246. You can tell right away that this is going to be significant. And the p-value that goes with this is 0.0006. Now the p-value is simply the output from normal CDF. I might as well just put it in here just for grins and giggles. Normal CDF. And I'll put in 3.2. So we're going from here all the way to the end of the tail. That's the part in red. You can hardly see it. 3.246, comma, 99, or 9, or whatever. Okay, now it's expressed in scientific notation. They rounded it up to 6. You can see you're going to move that decimal place 1, 2, 3, 4, 5. I'm sorry, 4 places to the left, which will put 3 zeros in front of the 5.8. And so that we can just round up to 6. Anyway, it's 0.0006. Okay. So there's all your mechanics. So remember, everything on the right is what you have to show. What's on the left is what you do to produce that. And your conclusion. With the p-value this low, we reject the null hypothesis. There is reasonable evidence, or there is evidence, that the true proportion of home team wins is greater than 50%. It appears there's a home team advantage in Major League Baseball. That's all context. Okay, now you have rejected the null hypothesis. Now you'll do a confidence interval, and hold on. Okay, so we're going to make a confidence interval. Now, this is pretty straightforward. You know how to make a confidence interval, and we're just going to make a confidence interval based on p hat. But notice we're not going to use the standard deviation that we use from the test. Instead, we're going to make a standard error, which is the estimation of the standard deviation of p hat based on p hat. So we make the standard error, because now p sub 0 has been rejected. So we don't know what p is anymore. So we're sending out a little search party for it, and that's our confidence interval. And we want a 95% confidence, so z star is 1.96. We get the margin of error, z star times the standard error. And we get our confidence interval. We write our conclusion. I'm 95% confident that professional baseball home teams win between 51.3 and 55.3 of the percent of the games. All right. And now here we are at the end. What if we don't reject the null? Okay. We fail to reject. Okay. We never affirm the null. Okay. All right. There's not enough evidence to reject the null hypothesis. There is no evidence of the alternative hypothesis, but that's as far as we go. Okay. Don't base your null hypothesis on what you see in the data. Okay. You've got to be, if you're honest about your testing, then you're gonna state your null hypothesis first and then get your data. And don't base the alternative hypothesis on the data either, okay? Don't make the null hypothesis what you want to show to be true. Okay, it's simply the status quo. Don't forget the conditions. Never accept, don't ever say the null hypothesis is true. If you fail to reject the null hypothesis, don't think that a bigger sample would be more likely to lead to rejection. Okay. A larger sample could have a completely different p-hat. Okay, and here's what we've learned. You want to be very specific about knowing all this stuff. And here's the vocabulary. Make sure you know this. We'll have a vocabulary test soon. Okay, that's it.